It's my pleasure to introduce Dr. Rick Wilder from University of Colorado Boulder Laboratory for Atmospheric and Space Physics. And his colloquium title is Magnetic Reconnection in the Earth's Magnetosphere from Local to Global Scales. And again, if you have a question, just raise your hand using that little hand tool down in the toolbar. And I'm going to mute myself and just turn it all over to Rick.
All right. Hi, everyone. I think everyone can hear me, I'm sure. Just to double check before I go too far. I'll take that as a yes, I guess. So, hi, everyone. My name's Rick Wilder. The past several years, I've been working on the NASA Magnetospheric Multi-Scale Mission. You can see in a little circle at the bottom. And so I'm going to talk a little bit about that, a little bit of some of my other research that's not involved with MMS, and sort of try to say how I think it all ties into this upcoming drive center that UT Arlington has to study interhemispheric asymmetries in the magnetosphere. So I don't know why it's not going to the next. There we go. So I'm going to talk a little bit about what magnetic reconnection is, why it's important, talk a little bit about the MMS mission, and then I'm going to start by talking about some of the local physics of reconnection that MMS has studied, and sort of especially the role of electric fields parallel to the background magnetic field in mediating that reconnection. And then I'm going to talk about some of the global science that is a consequence of reconnection, and what relevance that might have to the drive center. So, space physics is multi-scale, and the magnetosphere ranges from tens of meters all the way to hundreds of Earth radii. And in the heliosphere, you're talking, AU scale phenomenon sometimes as, solar flares and coronal mass ejections inflate. One process that is multi-scale is reconnection. It heats and accelerates particles in the local plasma population, but it also drives the circulation of plasma through the entire magnetosphere as well as in the ionosphere. And so we're going to be talking about a mission NASA launched to study magnetic reconnection, and I'm going to show how it can govern local electric fields and currents as well as its impact on asymmetries in geospace. So in magnetic reconnection, what is it? In plasma physics, if we're looking at really low density collisionless plasma, like what we see in the solar wind and the Earth's magnetosphere, where the mean free path is so large that we just treat it as no collisions, the plasma will actually carry the magnetic field with it. And so if you have two plasmas carrying magnetic fields that are anti-parallel in this example, what will happen is in a very small, thin layer, the magnetic fields will merge and diffuse together, reconnect, and form two new reconnected magnetic fields, which the fields being taught will lead to a jetting of plasma away from the region where reconnection happens. And so that's sort of a cartoon picture. You have the inflow, and then you have the outflow jets with the newly reconnected fields. So where does this occur? It causes CMEs, these little ribbon-like structures, to detach from the sun, which then expand into interplanetary space and can drive space weather at Earth. It can happen in accretion disks and lead to galactic jets, for those of you who are interested in astrophysics. Additionally, you can find it in the magnetospheres of pulsars and magnetars. And in controlled fusion, actually confinement devices that try to confine plasma using magnetic fields for fusion purposes will often break down and crash because of reconnection. Now, for the interests of this center, reconnection, the important part we're going to talk about is reconnection at Earth's magnetosphere. So the sun is constantly ejecting coronal plasma. We call that the solar wind. And the solar wind carries a portion of the coronal magnetic field with it. We call that the interplanetary magnetic field. If it's southward, it'll interact with Earth, and you can see it reconnects at the day side of Earth, and then carries open magnetic field lines over the polar cap and piles them into the tail of the Earth's magnetosphere. As pressure builds up in the tail, reconnection occurs again, and that brings electrons and protons along magnetic field lines into the Earth's ionosphere, which leads to the aurora. So here's sort of a cartoon conception of that cycle. So we have the interplanetary magnetic field is southward. The Earth's magnetic field is northward. They will reconnect. You will get taut magnetic fields that'll lead to a jetting of plasma and a carrying of magnetic flux over the Earth's poles in both hemispheres, where they will meet again in the tail, reconnect, leading to a jetting of plasma towards the Earth. And then these newly closed field lines will circle right back around to the day side of Earth, where the process will happen again. And so this stirs up large-scale global plasma convection at Earth. So what exactly is happening in reconnection? So generally what happens is you have these two plasmas carrying anti-parallel fields, and there will be a small region with an enhanced current where the magnetic field will diffuse across the topological boundaries. That's sort of where the reconnection occurs. It's where the magnetic field, quote unquote, breaks. And then eventually out of the diffusion region, you'll get your jetting of plasma. And the speed of that plasma jet is the magnetic field strength divided by the square root of the permeability of free space times the mass density of the plasma. We call that the Alfvén speed. Alfvén waves are like magnetic fields acting like vibrating strings. So it's sort of the phase speed of those Alfvén waves is also the speed of the jet. So we have several major regions, and this is where a lot of the jargon comes in. So we have the inflow, that's the plasma carrying the magnetic fields that flows in. There's a diffusion region where the fields break. There are the separatrices, these solid lines. That's sort of a surface, so you can view this as coming out of the screen. And those separatrices kind of separate magnetic field lines with different connectivity. So on one side of the separatrices, you have these inflowing plasmas and magnetic fields, and then you have a different magnetic connectivity on the other side of the separatrix. And then finally, we have the outflow. Sometimes we call that an exhaust jet. So if we zoom in, what's going on in the diffusion region? That's been one of the big mysteries of reconnection that people have been trying to solve since the 40s. And so if we zoom in, we actually see a much more complicated picture. So first off, the ions, which are typically protons in the Earth's magnetosphere, are much heavier than the electrons. They're more massive. And what that means is that they have a much larger radius about which they orbit around a magnetic field. Now, what that means is that they're much more likely to jump across the separatrix and into the outflow jet, whereas the electrons will bounce along the magnetic field and they'll have to get much closer before they jump the separatrix and jet out. And so that creates actually two diffusion regions, an ion diffusion region, that's the blue region, and an electron diffusion region. There's also an ion jet, which is much larger scale and typically slower. And then there's an electron jet in the ion diffusion region and the electron diffusion region that's often much faster. It's super alphanic. And this difference in the behavior of the ions and electrons sets up current loops, which creates these magnetic field perturbations. You can see they're quadrupolar, and we call those Hall magnetic fields. It's a Hall effect. And that'll be important when we start discussing why reconnection happens. So in the diffusion region, what we're really doing is deviating from the frozen-in condition. That's what I was saying earlier. In collisionless plasma, the magnetic field will convect with the plasma. But in the diffusion region, the magnetic field is diffusing into the plasma. That's what allows the different fields to reconnect. And so this happens due to terms in generalized Ohm's law. So in an ideal collisionless plasma, you would basically have no electric field in the frame moving with the plasma, and the magnetic field would be carried by the plasma. Now, one way you can get diffusion is if you have resistivity. This would be collisions between particles. So if you have a resistivity, you get to the classic Ohm's law that many of you have seen in an electrodynamics class. But there's a problem. First, resistivity, when you actually do the math, it predicts reconnection happening at a rate that is 2 orders of magnitude slower than what we observe on things like solar flares. Another problem is, in the Earth's magnetosphere, the plasma is effectively collisionless. So there can't be any resistivity because you don't get collisions between particles. So what we have to do is actually look at generalized Ohm's law, and what this is we take the momentum equation for electrons and look at every term in the momentum equation that can lead to a non-ideal electric field in the frame of the plasma. So the first term is the Hall term. That's due to that separation of the electrons and ions. And that was, if you include that, when we look at simulations, it actually agrees with the reconnection rates we can predict. However, if you look at J dot E, the dissipation associated with reconnection, this will be 0. So it doesn't actually contribute anything to the heating or energy dissipation. It just facilitates a faster reconnection rate. And so to really understand how reconnection is breaking, we actually have to go all the way down to the electron level, looking at the divergence of the electron pressure tensor and the electron inertial. This is the direct acceleration of electrons, the electric field associated with that. So that's sort of the big mystery of reconnection, is what facilitates the energy transfer, the electron pressure or the inertia, or some combination. So to solve this, NASA launched a mission called MMS. It's 4 spacecraft at a tetrahedral formation that probes the Earth's magnetosphere. Here it is at the magnetopause, the day side. And you can see they're spaced to try to probe down to this electron diffusion region scale. That's about, electron diffusion region is probably about 1 kilometer thick. The ion diffusion region, this is not to scale, is going to be like 100 kilometers thick. It's got 3D electric fields, and it captures electron and ion distribution functions, if you know your statistical mechanics, at 30 and 150 millisecond cadence. Previous space missions did this at 4 or 5 second cadence. So it's it's a couple order of magnitudes faster than any other plasma mission. And with the separation in the tetrahedron, we can actually evaluate Maxwell's equations and generalized Ohm's law. We can take divergences, curls, gradients, and actually probe the physics of reconnection. So before I start showing MMS data, I kind of want to get a little bit of jargon out of the way. First off is local LMN coordinates. So when we study reconnection, we rotate into a local coordinate system. L is in the direction of these anti-parallel reconnecting fields. It's also in the direction of the outflow jets. M is out of the page. That's in the direction along the current in the diffusion region and the reconnection layer. And then N is normal to the current. So that would be, crosswise here. Another term is something called guide field. So magnetic fields are rarely anti-parallel. In fact, they usually are at some finite angle with each other. And so when you rotate into the reconnecting plane, there will actually be a non-zero component of the magnetic field that's out of the plane. And that does not reconnect. In the olden days, some of the space physics people will know this as component reconnection, as opposed to anti-parallel reconnection where there is no guide field. Finally, I'll often say dissipation, and I don't mean dissipation in a irreversible sense. What I mean is conversion of the stored electromagnetic energy in these reconnection fields, the conversion of that to kinetic energy and heat. And that is simply J dot the electric field, the current dotted with the electric field in the frame moving with the electrons. So that's how we know there's electrons getting heated and accelerated. So let's see. So early on in the MMS mission, we made our first encounter with the with an anti-parallel electron diffusion region, or EDR. I actually found this event, and it was published in Science. It was the first major result from MMS. And so I'm going to walk you through this because you're going to see lots of stack plots that look like this. So the top panel is the magnetic field in L, that's the reconnecting component, M, that's the out-of-plane component, and N, the normal component. Then we have ion and electron energy spectra. The y-axis is energy. The x-axis is time. You can see it's about a minute and a half. And then the colors are fluxes of particles that the detectors measure. This is the number density of the plasma. This is the bulk velocity of the ions. And this is going to be one of the important panels because this is how we identify reconnection. Blue is the L. That's the direction of a reconnection jet. And then M is out of plane, and red is normal. This is the electron velocity perpendicular to the field. That's how we'll identify the electron jet. This is the current. This is the current measured by the plasma instrument. So it's based on the velocity difference between protons and electrons. This is the current using all 4 spacecraft to take curl of B. This is the electron temperature. Blue is parallel to the magnetic field. Red is perpendicular. And then finally, we have the electric field in that same LMN coordinate system. So we start off with a northward magnetic field. L is positive. L is mostly northward. And you can see that the plasma is much more tenuous. There's less flux, lower density. We then see that the L direction reverses in the magnetic field. And as it reverses, we cross into a layer with higher density. So we're going from the magnetosphere to the region of shocked solar wind that we call the magnetosheath. So we've crossed that boundary or current sheet where the magnetic reconnection can occur. That's right down here in the diagram. And as we cross, we see a southward enhancement in the flow. That's the reconnection jet. We then spend some time out in this magnetosheath, and then we see the smoking gun. We see a southward ion flow and then a northward flow, which means we cross the reversal of these jets. Right in the reversal, we see a sudden enhancement in the electron velocity. So we've crossed the electron jet. Additionally, we see very strong electron heating. We see a very large amplitude current from both the particles and the curl of B. And we see enhancements in the electric field. So if we really zoom into this, we see that, first off, the out-of-plane electric field decouples from the motional electric field due to the plasma. That means we've broken that frozen-in condition for the electrons. That means this is the electron diffusion region. What we see there is very strong dissipation. You can see it's decomposed to contributions from currents and electric fields perpendicular to the magnetic field and parallel to the magnetic field. So you can see it's mostly perpendicular. And one thing that we found that was a surprise is these electron distributions. So these are velocities perpendicular to the magnetic field in both directions. Now electrons, as you know, want to sort of orbit around the magnetic field in a circular motion. And that circular motion means it's gyrotropic, it's uniform. However, so what we would expect to see is a ring-like distribution like this if we were looking at electrons, but instead we see a crescent. And that crescent is because those electrons are bouncing across this diffusion region, and in phase space it traces out this crescent shape, and that leads to a divergence of the pressure tensor. If we go all the way back to generalized Ohm's law, it leads to off diagonals of the pressure tensor and a divergence, which can break the frozen-in condition and heat the electrons. So it seems like the electron pressure is guiding the reconnection, but not so fast. What happens if there's a guide field? This is an anti-parallel case. What if the magnetic fields aren't perfectly anti-parallel? So this is another case we found early on. I worked on this with Stefan Eriksson, one of my big collaborators at LASP. And we found another electron diffusion region. It's in a complex region, so I'm not going to walk you too much through it. But what I do want to point out is that we see many of the same signatures as the anti-parallel. Here we have the BL in green, that's that reconnecting component, and you can see it reversing. But you can see there's a very large background magnetic field when that BL reverses. And we see the very large current. We see the parallel heating of the electrons. But one thing we do see is a very large electric field parallel to the background magnetic field. It's almost 15 millivolts per meter, whereas if we go back to the earlier event, if I can, you can see it was closer to 2 or 3 millivolts per meter here. So we get a very large electric field parallel to the background field. Even more interestingly, no crescents. The electrons are gyrotropic. They're orbiting around the magnetic field as normal. And that's probably because you have such a large background magnetic field. They actually never break the frozen-in condition. They just get heated. Instead, what we see is parallel acceleration. This is energy parallel to the magnetic field and perpendicular. This is outside of the diffusion region. This is inside. And we see this big blast of parallel electrons. So this is not reconnection is not being caused by agyrotropy in this case. It has to be caused by either electron inertia or some sort of unidentified parallel pressure gradient. So the question we have is, what's the general trend? So reconnection is hard to capture the dayside magnetopause. You're hitting a huge area in a small space. But what we can do is look in the Earth's magnetosheath. The solar wind gets shocked and slows down to a subalphanic and subsonic speed. And it's a highly turbulent region. And in all of these turbulent eddies, you can get localized reconnection. So I went through and started looking at times when MMS was in the magnetosheath. And I was looking for times when MMS crossed either the electron jet or the electron diffusion region. And here's an example. So again, we have our ion spectra and electron spectra. And you can see that we see a reversal of our BL, that's this field here. You guys can see my cursor, right? I've been pointing to stuff with the cursor, and I don't know if it does that on Teams.
It does.
Okay, great. So you can see a reversal in BL. So again, we're seeing that reversal and reconnection, or a current sheet at least. What we also see, again, is that enhancement in the electron temperature. We actually don't see an ion jet, or much of one. We see a slight enhancement in the ion velocity in the L direction. And so that suggests we're nowhere, we're closer to the diffusion region, especially because we do see an electron jet. So as MMS flies through, we see this blast of electrons that's faster than the local alphane speed. Additionally, we see a bipolar structure in the magnetic field. That's that Hall field where you see the electrons and ions decouple. This is a moderate guide field event. So in the large guide field event, it was 3 times the reconnecting field. Here it's about half. You can see right here in the middle, we still have about half the field amplitude left. But what we see is the same as the high guide field. We see very large parallel electric fields. And the dissipation is almost entirely due to currents and electric fields parallel to the magnetic field. So it's much more like the high guide field than the anti-parallel case. And if I go forward, when we look at the distributions, here's our perpendicular distributions. You can see we do see crescents here, but they are much weaker than the crescents we saw for anti-parallel reconnection. So if I show another example, this is a more anti-parallel event. You can see that the magnetic field goes to almost 0 when it reverses. We still see the electron jet, still no ion jet. We see enhanced heating in the electrons, large out-of-plane current, very little parallel electric field, just like that original event. Additionally, the dissipation is all due to fields and currents perpendicular to the magnetic field. So what I did is I went and found many of these types of events in the sheath, about 13 of them, and I wanted to see, where the change happens between this parallel-dominated and perpendicular-dominated regime. So what I did is I took a J dot E ratio for each event. So what I did is I looked at the J dot E due to fields and currents parallel to B, and the J dot E due to fields and currents perpendicular, and normalized them to the maximum dissipation to see which dominated. And so for all events, what we can see is, so this is that ratio. The top, if you're above 0, it means that parallel fields and currents dominate, and it's probably a more inertial-like regime, whereas the bottom means perpendicular fields and currents dominate, and so that means it's a more pressure-like regime. And what you can see is that with guide field even less than half of the background of the reconnecting field, you actually see an inflection point. So it jumps to parallel-dominated physics very quickly. If there's even a little bit of magnetic field left, you will get a jump to that different regime. And so parallel electric fields are very important to reconnection. And so going back to Ohm's law, is it the pressure or the inertia? And what kind of pressure? The answer is it really depends on the geometry of the reconnecting magnetic fields. And so that's a new discovery by MMS that hopefully will help us better understand and predict how reconnection occurs. So to summarize this first part, magnetic reconnection is governed by physics that's different depending on whether the reconnecting fields are anti-parallel or at an angle less than 180 degrees. The dynamic shift.
I'll go for a walk.
Oh, I think someone should mute. So the dynamics shift very quickly, and this shows that reconnection is very efficient at generating field-aligned currents and field-aligned electrostatic potential drops. This could be potentially important for the larger scale current systems in the magnetosphere. And it's a multi-scale process, so I'd like to shift gears to global consequences. So why do we care about reconnection? Well, if we go back to the big picture, this is that Dungy cycle where you reconnect on the day side and close in the tail. That drives dynamics throughout the magnetosphere and in the ionosphere. So this is looking at the polar ionosphere. This circle is about 60 degrees magnetic latitude. This is where the aurora would be. The aurora kind of looks like an oval if you look from space. And that auroral oval also acts as sort of a boundary between open and closed magnetic fields. So we have a field here, would be roughly here. It's closed. Then it reconnects, and that the foot point of that field crosses this open-closed boundary, flows over the polar cap. You get reconnection in the tail. It crosses the open-closed boundary again because it recloses and circulates. So when you look at the auroral oval and you look at the flows which are associated with the foot points of these fields, you can use the ionosphere as a window to see the global magnetosphere as well as the foot points of magnetic reconnection. Now, what happens if the magnetic field in the solar wind is pointing northward? Well, it's no longer anti-parallel at the day side. Although, as I showed, it doesn't have to be anti-parallel. You can actually get lots of reconnection, and we've been seeing that with MMS. But where you get most reconnection is actually closer to the poles, in these lobe tail magnetic field lines that are open poleward of the cusp. And that leads to these jets that move sunward, and so you actually see reverse sunward convection. Now, the polar cap will become highly contracted, and its boundary location depends on a variety of factors, which I'll go into. First off, this image is an equinox image. It's ideal, and it assumes reconnection happens simultaneously in both hemispheres. But what happens if you're at solstice and the summer hemisphere, which in this case is north, is tilted towards the sun? Well, reconnection can occur first in the summer hemisphere. It could happen between the interplanetary magnetic field and an open field line, or the interplanetary magnetic field and a closed field line. And that'll lead to two different topological configurations. Then it'll happen in the winter hemisphere. So if it reconnects with a closed field line, you get an over-draped open field line on the day side that'll reconnect in the winter hemisphere. And it can reconnect with an open field line in the winter, or it could reconnect with a closed field line in the winter. And so that leads to a very complex structure in the polar cap. And you can see, this is the solid lines are the convection flow patterns. The dashed lines are the open-closed boundary. And you can see that there's much more open field in the summer hemisphere, or I shouldn't say more open field because the divergence of B is 0. There's much more plasma flowing on open field lines in the summer than in the winter. And why is this important? Well, I was doing interhemispheric observations back when I was in graduate school. This was a strongly northward IMF event. So we would expect reverse convection in both hemispheres. And it was there was a large dipole tilt, which means that you have the southern hemisphere is in the summer, and so we might see reconnection first. So I was looking at the convection patterns, and each one of these equipotentials is about 2 kilovolts. And what we saw here are the reverse convection cells, like in my early cartoon, and this is observed by a ground radar that measures plasma flows, and then we fit it to a spherical harmonic to get an overall pattern. What you can see is that the equipotentials and streamlines are, much more clumped together in the southern hemisphere. That means there's a much larger voltage drop across the flow and much faster flows. And so we were actually expecting the voltage to be larger in the winter because it has lower conductivity. So we wanted to know why. So what we did is we used Defense Meteorological Satellite Program data. These are electrons and protons. They're looking up the magnetic field at electrons and protons coming down at you. And so what you can see is here, these are auroral electrons and protons. And when we see those auroral electrons drop out to background levels as the protons drop out, we say that's the auroral oval. That's the open-closed boundary. So we did this for the summer hemisphere. You can see it's larger. We did it for the winter hemisphere, and you can see it's much narrower. And when we map it on the flow patterns, we can see that much like that cartoon I showed you earlier, there's a lot more circulation on these open field lines in the summer. So there's a lot of open flux being stirred up. So we decided to simulate this. This is a model that I think people at UT Arlington use a lot. It's a magnetohydrodynamic simulation. It solves a combination of Maxwell's equations and the Navier-Stokes fluid dynamics equations. So this is a simulation of that event I observed. Here's the magnetosphere. You can see there, the color is flow speed. So you can see jets going in different directions from these 2 points. So that's where our reconnection X line is. And we can see that there's an overdraped field line associated with reconnection happening first in the summer, just like in the cartoons. But what was really surprising is all this stagnant open flux in the winter. So all this flux opens in the winter, and a lot of it doesn't seem to reconnect. And when we look, our simulations actually look a lot like the observed data. You can see that there's much more circulation on open field lines in the southern summer hemisphere, and you see a larger voltage, which is the dashed line in the southern summer hemisphere. So it looks like, and so if we look out in the magnetosphere, here on the top we have field lines traced through the southern hemisphere to look at the reconnection there, and you can see lots of these overdraped fields. Some of them look like they reconnect in the winter, but there's just a lot of stagnant open flux that never reconnects in the winter, or is just waiting to be closed by these overdraped fields. And so you can see this from another angle. This is looking at the Earth straight from the sun. You can see all these overdraped flux, some of which will circulate around and never reconnect. So the overdraped flux just keeps circulating in the summer while it just sits there in the winter. And so this reconnection interchange cycle that's interhemispheric can actually create asymmetries in how the ionosphere behaves and convects. And that's just due to the topology of the magnetic field and where reconnection is happening. So it has very little to do with conductivity, and we tested that, and the asymmetries remained even when we used constant ionospheric conductivity. So this is an example of how reconnection, understanding reconnection, can help us understand hemispheric asymmetries in the ionosphere. If we know where reconnection occurs and how it can occur, we can start to predict how that might change the structure of the ionosphere. And this could also be associated with strong Dawn-Desk interplanetary magnetic field or a strong sunward or anti-sunward interplanetary magnetic field. So some final thoughts looking ahead at this new drive center, which is studying hemispheric asymmetries in geospace. This shows you could actually get hemispheric asymmetries just by magnetic field topology and reconnection happening in different places in different hemispheres. But it can also be driven by asymmetries in the geomagnetic field, conductivity differences in different ways. And so having a holistic picture can really help us understand these asymmetries. And, in addition to simulations, we need observations both in the magnetosphere and in the ionosphere and in the ground to really iron these out. And we need a lot more events. I only looked at one event here. So how can MMS help? MMS has been up for 5 years now. It's spent a lot of time skimming the magnetopause. So we have tons of observations of the magnetopause. And that's one of the inputs to the geospace system. So if we see something in the magnetopause, we could trace it down to the ionosphere and look at the hemispheric differences. Additionally, we've raised the apogee in the last 3 years. So we're now way further out. So we target the tail, we target the bow shock, we target the solar winds. And those are also all inputs to what we can see when we look at, the different poles. And additionally, because it's multi-spacecraft, we can evaluate Ampere's law, and we can do that even when MMS is not collecting the high-rate data. So we can really map electric currents all throughout the magnetosphere, which will be really important for MI coupling. And then, of course, my other background is ionospheric observations. I have a lot of experience with these super darn radars that can provide us maps of the convection. I have experience with the Ampere Iridium satellites. They all have magnetometers, and they can evaluate, and then you can actually evaluate Ampere's law and measure currents, electric currents going into and out of the magnetosphere, which we could then compare to in situ observations from MMS. And so this can provide global and mesoscale information, and they're great for comparing with models. So we can really attack multiple scales using multiple instruments. And so I'll leave my conclusions up so that people can start asking questions.
Okay, thanks very much, Rick. And so now we're open to questions, and just use your raising hand tool to indicate that you would like to ask a question. And so we can see who's got a question. Anybody have a question yet? I've got to look and see if I can scan through all of this.
If you don't mind, I'm just going to have a throat drop. My voice is hoarse from talking all day, 2 days.
So Dave Nygren has a question. So Dave, you can unmute yourself.
Hi there, Rick. I have a question because I'm a naive particle physicist. Once you understand these asymmetries and reconnection, what should a naive person like me conclude? I mean, what level of understanding has really been achieved?
Well, so, a big goal in space physics, I think, is being able to predict the behavior of the system, based on what we know coming from the sun and in the solar wind. And so, one of the big obstacles in making those predictions is predicting magnetic reconnection, is predicting where it might happen, etc. And so what we're really moving towards is predictive capabilities, we hope, where we can treat, the behavior of the Earth's magnetosphere the way meteorologists treat weather. Space weather, they sometimes call the field. But it's essentially enabling our ability to predict the magnetospheric activity, which in turn will help us better predict its societal impacts, its impacts on technology and satellites and etc. So,
okay. Thank you.
Mm-hmm.
I was muted. Sangwook Park has his hand up, so you're next.
Hi, this is Samuel Park, and I'm an observation astronomer. I just realized that what you were talking about, the magnetic reconnection, is exactly what those astrophysicists use to explain the radiations from neutron stars, particularly from magnetars. So probably it's a little bit off kind of question, but I was just curious if you, by any chance, if you are interested or can work on the electromagnetic spectrum, radiation spectrum coming out of those magnetic reconnection activities that we can observe outside of the magnetosphere rather than inside of the magnetosphere. So,
well, the astrophysical applications are interesting because you do observe them so distantly, and the physics is different too, because I think often you'll have the Alfvén speed will approach the speed of light, or so I think in some astrophysical cases you can get pair plasma reconnection and all sorts of stuff. So as far as observing them remotely, you mean like at Earth, observing Earth the way one might observe a star, or
right? Yeah.
So I think Ramon is involved in. There's a Chinese mission called SMILE that I think it's China and the EU joint that is using X-rays to try to take a snapshot of reconnection at the dayside magnetosphere. I think Ramon knows more about that mission than I do, but there are ways to observe it remotely as well. Yeah.
Okay. But you don't calculate, for example, the electromagnetic spectrum that may be predicted from those magnetic reconnection activities as observed from a distance. You rather work on the data taken by those satellites inside of the magnetic sphere.
Yeah, I've mostly been looking directly in situ. Now, we do see a lot of waves, electromagnetic and electrostatic, right near where that diffusion region happens. But it's all in situ is mostly what I've been looking at, yes.
All right. Thank you very much.
Yeah.
Okay. Are there any other questions? So, Rick, I have a question for you.
Sure.
You showed very convincingly the difference in the ionospheric effects of the asymmetric impact of reconnection when you've got a significant dipole tilt, and that will produce asymmetric currents, and presumably then asymmetric ionospheric heating, and how would that be a potential interest for space weather?
Yeah, so with the ionospheric heating, I'm thinking back to that old GEM focus group on the dayside field-aligned currents and energy deposition. If you get higher potentials and faster flows in the ionosphere, that's more collisions, higher Joule heating rates, which can lead to upwelling of plasma. And I did some study when I was a postdoc of Joule heating rates with respect to the open-close boundary, and where they tend to occur and what that tells us where they map in the magnetosphere. And I do remember for strong BY, for example, that you would often see the enhanced Joule heating on those first merging cells just inside the open-close boundary. So it really was at the foot point of the magnetic reconnection. And so I can imagine that if you have one hemisphere that's more stagnant than the other with respect to reconnection and opening fields and what have you, you might end up getting lower Joule heating rates, would be my suspicion, but I'd love to test that hypothesis.
Good. Yua, you have your hand up.
Hi. Oh, thank you for showing the exciting result from the MMS mission. And I have two quick questions to you related. First of all, can this mission separate the spatial and the temporal variability? And go ahead. Yeah, maybe.
Oh, no, I'll let you do both. I'm sure they're related.
The second one is, can the the result from the MMS mission help the simulation of the reconnection or not? How the simulation, how the observation result help the simulation of the reconnection? Do you have any idea?
Sure. So for the first question, so MMS was designed to resolve spatial and temporal differences. It's got a very tight formation, although actually MMS is separating slowly. We're going into extended mission, and we've kind of beaten the electron scale physics to death. So we're starting to separate out. We're also going to experiment with some string of pearls formations, which means it would punch through different regions in sequence rather than as a tetrahedron. And so all of those, depending on the scale size of what you're looking at, you can separate spatial and temporal variation. We often will use techniques to calculate the speed of structures that as they flow past the spacecraft, for example. As for your second question, the MMS has worked very closely with the theory and modeling community. One of the big things that the models tend to underpredict are those amplitudes of the electric fields parallel to the background magnetic field. We consistently see almost an order of magnitude larger parallel electric fields, and it has kind of informed us on some of the limitations of those simulations, like particle and cell. They assume an electron to proton mass ratio that's not necessarily realistic because it conserves computing resources. And we think some of the discrepancy might be due to that. And, models can really help guide our results. And it would be really interesting for a global magnetosphere model. I'd really like to, I know people are starting to add, kinetic models at the reconnection sites to global models. And I'd really like to see more of that because I think that would be interesting to see how things change.
Good. Jay, you've got your hand up.
Yeah. Hey, Rick.
Hi.
Thanks for the nice talk. So you might have already discussed this during your presentation, but how long does this MMS mission last, and what comes after this?
So the Prime mission, so it launched in 2015, and the Prime mission was until it was basically through the fall of 2017. So we're on our first extended mission. So it's been 3 years since the Prime mission has been over. We're putting in a senior review proposal for another 3 years. Usually each extension, the funding goes down a little. We're hoping that MMS will keep kicking for 10 years. So
10 years.
Yeah, at least. We do eventually have to deorbit at some point. NASA no longer lets us leave junk in space, but I would love to see it keep going.
So these guys will continue taking data, increasing the statistics. Right?
Yes.
So that will improve your that will improve your uncertainty.
Oh yeah, definitely. And we can start making maps of some of the quantities we measure. I'm especially thinking of, as I mentioned, those the electric currents. The fact that we have the capability to calculate curl of B, on the fly. We could really start making really detailed maps of electric currents in the magnetosphere. I think that would be something that people are going to start looking at more in the future, and I think some people already have started.
But they're in the fixed location, aren't they?
So if you go, let me go back to as the Earth. So this is looking. So actually, this is a little bit of a misleading diagram because the orbits are actually in the equatorial plane, not polar. They just did this to show, what the orbits might look like. So what happens is throughout the year, as the Earth orbits the Sun, the apogee of the mission sort of swings around the Earth. So it covers the day side, the night side, and the dawn and dusk. And in orbital dynamics, I think they call that the J2 term of the orbit. Mm-hmm. So it doesn't stay fixed. It takes about a year to make a full circulation around the Earth.
Mm.
Usually in the winter is when it's on the day side, and in the summer is when it's on the night side.
So suppose it lasts for 10 years, and there must be some plans of the mission after that, right? Because 10 years is not a long time to build something and put them up there.
Yeah. Well, I mean, really it's hard to predict how long, a mission stays funded, and you're constrained by how much fuel you have left, because you need enough fuel to deorbit. But some missions, the European Space Agency launched Cluster, which MMS was partially modeled after. It was 4 spacecraft at much larger separation. They launched that, I think, in around 2000, and that's still collecting data. So they can last
after 20 years.
Yeah.
All right. Okay. Thanks.
Yeah. No problem.